Welcome back to the deep dive. We're continuing our journey through mathematics today.
And we got a really interesting one. It looks like a simple puzzle on the surface.
Yeah, exactly. It's about, well, can you take a square, just a plain square, and cut it up?
Into triangles.
Right, into triangles. But here's the kicker. An odd number of triangles, and they all have to have exactly the same area.
It sounds plausible, doesn't it? Like something you could just, fiddle around with and figure out. Very intuitive question.
Totally. We often break shapes down, and triangles are basic building blocks. Equal area seems like it should be manageable. But this little problem, it actually tripped up a math professor back in 1965, Fred Richmond.
Oh, really?
Yeah, he was apparently thinking about it for like a graduate student exam or something, but he couldn't crack it himself.
Wow. That tells you something right there. If a professional mathematician found it tricky.
Right. He ended up publishing the question in the American Mathematical Monthly, basically asking the community, hey, can anyone solve this? It hints that there's definitely more going on.
It really does. It's a perfect example of how these, seemingly elementary geometry questions can hide some really deep mathematics.
So it wasn't simple after all. And 5 years later, 1970, Paul Minsky steps in.
I.S. Minsky.
And he delivers the answer, Minsky's theorem. And it's pretty definitive.
It is. The theorem states, quite simply, that a square cannot be divided or triangulated into an odd number of triangles of equal area.
Cannot. Full stop. Impossible.
That's right. You can do 2 triangles, sure. Just draw a diagonal.
Or 4. Draw both diagonals.
6 is possible too, with a bit more work. But 3, 5, 7, any odd number. Minsky says no. It's what we call a non-existence theorem.
It's kind of mind-bending when you first hear it, because you instinctively think, well, surely if I just keep adding lines, rearrange things.
You think you could eventually make it work for, say, 5 triangles.
Yeah. But no, it's fundamentally impossible. A hidden rule about squares, I guess.
And the really amazing part is how he proved it. The theorem statement is pure geometry, right?
Right. Dividing a square.
But the proof, it pulls in tools from, well, completely different areas. Number theory and combinatorics.
Okay, wait. Number theory, like properties of integers and primes.
Exactly. And combinatorics, the math of counting and arranging things. Specifically, Minsky used something called the p-adic absolute value, combined with Sperner's lemma.
Wow. Okay, that sounds sophisticated for cutting up a square.
It is. It's a brilliant example of mathematical connections you wouldn't expect.
Let's try to break that down a bit. The p-adic absolute value. What is that, roughly? How does it even relate?
Okay, so usually when we think of the size of a number, we think of its distance from 0. Like 5 is bigger than 2.
Sure, the normal absolute value.
Right. The p-adic absolute value is totally different. It measures size based on divisibility by a specific prime number.
P-adic apps.
Divisibility, how does that work? Well, think of p as your chosen prime. Let's say p equals 2. The more times a number is divisible by 2, the smaller its two-adic absolute value is.
Smaller. So like 8 is divisible by 2 3 times.
Right. 8 is 2 cubed, so its two-adic absolute value is 12 cubed, which is 18.
And 4, that's 2 squared.
Its two-adic absolute value is 12 squared, 14. See, higher powers of 2 get smaller.
Okay. What about odd numbers like 3 or 5? They aren't divisible by 2 at all.
Their two-adic absolute value is just 1. So in this two-adic world, odd numbers are bigger than, say, 16.
That is really, really counterintuitive. My brain hurts a little.
It takes some getting used to. It's a completely different way to view numbers.
So how does this weird size, based on divisibility by 2, help with the triangles in a square? It feels like miles away.
This is the genius part. Minsky zeroed in on p2, the two-adic value. And here's a key fact. For integers, the two-adic absolute value is less than 1 if and only if the integer is even.
Ah, okay. Less than 1 means even. Equal to 1 means odd.
Exactly. This property becomes a tool to somehow detect the evenness or oddness related to the areas of those triangles.
Okay, I'm starting to maybe see a glimmer of a connection. Even odd number of triangles.
All right.
What about the other piece? Sperner's lemma. You said combinatorics?
Yes, Sperner's lemma. It's a result from combinatorial topology. Let's simplify. Imagine you've tiled a shape, like our square, with small triangles.
Okay, a triangulation.
Yeah. Suppose you color every corner, every vertex in this whole picture using 3 different colors. Let's say red, green, blue.
Right.
And suppose you follow some specific rules about how the colors have to appear on the outer boundary of the original square.
Like certain corners of the square must be certain colors?
Something like that, yes. If those boundary conditions are met, Sperner's lemma guarantees that somewhere inside your tiling, there must be at least one small triangle that has one vertex of each color. A red, a green, and a blue vertex.
A rainbow triangle, you could call it?
Precisely. It guarantees the existence of this special kind of triangle, just based on the coloring rules.
Okay, so we have this weird two-adic number thing that knows about even and odd, and this combinatorial thing that guarantees a rainbow triangle if we color things right. How on earth did Minsky link them?
This is the magic. Minsky invented a way to color every single point in the square, including all the vertices of all the little triangles, using 3 colors. But the coloring rule wasn't arbitrary paint.
No. What was it based on then?
It was based entirely on the two-adic absolute values of the point's x and y coordinates.
Whoa. Okay, so the color of a point depends on the two-adic size of its coordinates.
Exactly. He divided the whole plane into 3 sets, or 3 colors, using rules derived from two-adic valuations. It's a number-theoretic coloring scheme.
That is incredibly clever. So you apply this two-adic coloring to all the vertices in the square triangulation.
Yes. And because of how he defined the coloring, especially how it behaves at the corners of the original square,
Yeah.
0, 0, 0, 0, 0.
Assuming the square goes from 0 to 1, yeah.
Right. The boundary conditions for Sperner's lemma are met automatically by this two-adic coloring.
So Sperner kicks in.
And guarantees that there must be at least one triangle in the subdivision whose 3 vertices have 3 different two-adic colors. A rainbow triangle exists.
Okay, so we're guaranteed one of these special triangles. What's special about its area?
This is the next crucial step. Minsky then proved, using the properties of the two-adic values, that any triangle whose vertices have these 3 different two-adic colors must have an area, let's call it A, whose two-adic absolute value A is greater than 1.
Greater than 1, okay. Remember, for two-adics, that means the denominator must have more factors of 2 than the numerator. Essentially, it relates to being odd in some sense, right?
Well, let's hold that thought. The key is A or O for this rainbow triangle.
Got it. So let's put it together. We assume we can divide the square into M triangles, where M is odd.
Right, the starting assumption we want to break.
And they all have the same area, let's call it A. If the square has area 1, then M times A equals 1.
Correct. So the area of each triangle is A equals 1 meter.
Now, Sperner's lemma, via the two-adic coloring, guarantees at least one triangle, our rainbow triangle, whose area A satisfies A1.
Yes, but wait, in our setup, all triangles supposedly have the same area A equals 1 meter.
Oh, so that special rainbow triangle must also have area A equals 1 meter.
Exactly, which means its area A must satisfy A1.
So we need 1 meter as to be greater than 1.
Yes. What does that tell us about the two-adic absolute value of ni itself? Remember, 1 meter up 1 meter.
If 1 meter A1, then meter rows must be less than 1?
Precisely. And what did we say earlier about the two-adic absolute value of an integer being less than 1?
It means the integer has to be even.
Bingo. So the assumption that we could divide the square into equal area triangles forces the conclusion that it must be even.
But we started by assuming was odd.
And there's your contradiction. The initial assumption leads logically to its opposite. Therefore, the initial assumption must be false.
So a square cannot be divided into an odd number of equal area triangles.
Wow. That's Minsky's theorem, proven using this incredible blend of number theory and combinatorics.
That's genuinely beautiful, using such abstract tools, this p-adic stuff, to solve such a concrete visual problem.
It really is. And remarkably, as far as anyone knows, this is still the only known proof. Nobody's found a purely geometric argument, for example.
That highlights how unique and powerful Minsky's insight was.
Absolutely.
And you mentioned this didn't just solve the problem, it sort of opened up a new area, equidissections.
That's right. It spurred interest in similar questions.
Yeah.
Can you divide other shapes, like, say, a regular pentagon, into an odd number of equal area triangles? What about higher dimensions, like dividing a cube into equal volume tetrahedra?
So generalizing the idea.
Exactly. There are results now for hypercubes, thanks to Meade, and for regular polygons with 5 or more sides, thanks to Casamatas, often using similar, p-adic valuation techniques.
Fascinating. It all stemmed from this one seemingly simple question about a square.
It really shows the interconnectedness of mathematics. You pull on one thread, seemingly simple geometry, and you unravel connections to deep number theory.
It makes you wonder, doesn't it? What other basic questions are out there, just waiting for someone to look at them with the right, perhaps unexpected mathematical lens?
Indeed.
Yeah.
Perhaps something for you, the listener, to ponder. Think about the hidden mathematical structures that might govern even the simplest things we see around us.
A perfect thought to end on. Thank you. This was a truly insightful deep dive.